This is real-time laser Doppler imaging of the retina by ultra-fast GPU rendering of holograms. Eye conditions are major global health issues that demand continuous improvements in monitoring devices. Ophthalmologic imaging has been revolutionized over the past 2 decades by optoelectronics, and it has driven the current evolution of eye care. Digital holography heralds a new global transition to digital ophthalmology, which will allow the transfer of analog optical methods to the digital realm. Advances in ultrafast cameras and GPU computing power fuels the development of non-invasive eye imaging techniques that will predictably drive that transition. An experimental demonstration of real-time and sustained high-throughput holographic imaging of the eye is reported in this video. Computational hologram rendering and Doppler fluctuation analysis allow real-time and low-latency visualization of blood flow in the vascular networks of a human retina from a stream of optically acquired interferograms at a rate of about 2000 frames per second, which is about 2 GB per second. Doppler holography requires computationally intensive transformations of fast-rate image streams of optically acquired interferograms. The need to avoid any frame drop in order to ensure data integrity for uninterrupted Doppler image rendering in real time is technically very challenging. Our approach relies on sequential spatial and temporal transformations applied to batches of 32 consecutive interferograms converted to single precision complex valued arrays of 128 megabytes. These operations are used to perform optical wave propagation and temporal signal demodulation, respectively. Each frame batch undergoes a 2-step parallel processing. First, a spatial transform creates a hologram from each recorded interferogram. This operation is applied in parallel for each frame of the batch via the CU-FFT data shaping function XT-plan-many. The critical part of wave propagation, which creates a hologram from each interferogram, is computed by a fast Fourier transformation with CU-FFT in 0.97 milliseconds. Second, the temporal transform of a 32-frame batch of holograms is done by principal component analysis, which is achieved in practice by data eigendecomposition. The cuBLAS and the CU solver libraries were used for these matrix operations. In particular, the construction of a covariance matrix of a batch of holograms, its eigendecomposition, and the projection of the result into a subbasis were performed in 3.10 milliseconds. For an input throughput of about 2000 interferogram frames per second, image rendering and visualization reached about 60 frames per second. This demonstration was performed with an Adimec Quartz camera, a Bitflow Cyton framegrabber, and a NVIDIA RTX Titan GPU with Cuda 11 on Microsoft Windows operating system. Frame transfers to the device and processing by batches resulted in performance improvements with respect to frame-by-frame hologram rendering. EnSight enabled fine-tuning of the computation pipeline, which resulted in limiting the required time-consuming memory allocations in GPU, memory transfers, and synchronizations between the host and the device to the minimum. The current throughput bottleneck is host-to-device memory transfers of input frames from high-speed cameras to the GPU, which indicates that higher input throughputs may be reachable using GPU direct technology.